Imagine a universe not as we know it now, but as it may be in the most distant future imaginable. A universe that is cold, silent, and endless. All stars have faded. All light has gone out. Galaxies have long since dissolved, and time itself feels like a slow whisper in an eternal night. In this infinite darkness floats a single particle, a proton. Not part of any atom, not warmed by any star. Just one solitary proton, adrift in the black ocean of time. It is the last of its kind, the final remnant of a cosmos that once burned with light, life, and motion. If this proton could think, perhaps it would remember. It might reflect on the furnace of its birth, in the first fire of the universe. It might recall the stars it helped forge, the planets it once traveled through, the lives it quietly touched as it became part of oceans, cells, and memories. It has lived for longer than any human mind can comprehend, trillions upon trillions of years. And now, at the edge of time, this ancient particle sits in perfect stillness. But how did it get here? What story does it carry within? To understand the final moment, we must return to the very beginning, to the very first second of the universe itself. To understand the journey of our final proton, we must travel back through time, not billions, but trillions of years into the past. Far beyond the oldest galaxies, before stars had formed, before atoms had cooled, even before light could move freely through space. We must return to a moment so close to the beginning that it escapes ordinary comprehension. A moment not long after the universe came into existence, an explosion not of matter, but of space and time itself. What we call the Big Bang was not simply a bang. It was a transformation of nothing into everything. From that primordial fire, the laws of physics emerged, and so too did the seeds of matter. At just a fraction of a second after creation, less than a trillionth of a second, the universe underwent a dramatic and mysterious phase called inflation. Space itself expanded faster than the speed of light, stretching quantum fluctuations into the vast structures we observe today. Then, suddenly, this rapid expansion ended. The energy of inflation was released into the newborn universe, filling it with a storm of raw particles, quarks, leptons, photons, and neutrinos. It was a universe of pure fire, a seething plasma hotter than anything that would ever exist again. Amidst this chaos, the universe kept expanding, and as it did, it cooled. Within just a millionth of a second, temperatures dropped low enough for the strong nuclear force to act. This force, one of the four fundamental forces of nature, began to bind quarks together. Out of this process, something new emerged. Clusters of 3 quarks stabilized into protons and neutrons, and among those first protons was ours. It had no consciousness, no identity, and yet it was about to embark on a cosmic journey spanning the entire life of the universe. This was its birth, silent, elemental, and woven into the fabric of creation. But the early universe was not yet a gentle place. It remained dense and wild, filled with collisions and transformations. Neutrons and protons constantly flipped identities through interactions with other particles, their roles interchangeable in the heat of 1,000,000,000,000 degrees. Yet, time was already running out for this nuclear dance. Just 1 second after the Big Bang, the universe cooled further, down to about 1,000,000,000 degrees Kelvin. Collisions slowed, particles settled into their stable forms, and the strong force took hold again. This time, it began forging the first atomic nuclei: hydrogen, helium, and traces of lithium. Our proton did not remain alone. It was bound together with another proton and 2 neutrons, forming the nucleus of helium, the second most abundant element in the cosmos. Inside this tiny helium nucleus, an intricate dance began. The strong force held the particles together, while quantum mechanics allowed them to morph into one another, proton to neutron, and back again, trillions of times every second. For the first time, our proton had a home, a place of belonging within the building blocks of everything yet to come. Galaxies, stars, planets, and perhaps life itself, all would one day form from these tiny beginnings. It is humbling to consider that something so small, so ancient, and so simple could carry the memory of creation. Our proton was there when time was still young, when the laws of nature were being written in the language of heat and energy. It was forged in the first fire, in the chaos that followed the silence of the void. And though it could not know its destiny, it was already set in motion. From this moment of origin, the proton would travel through star and storm, through death and rebirth, across aeons of cosmic change. And its story, our story, was only just beginning. For hundreds of thousands of years after the Big Bang, the universe remained a hot, glowing ocean of plasma. In this primal sea, atomic nuclei drifted alongside free electrons, bathed in an intense bath of radiation. Although protons and neutrons had already bound themselves into nuclei, electrons could not yet join them to form atoms. The universe was simply too hot. Any attempt to combine would be shattered instantly by the searing energy around them. Light, too, was trapped, constantly scattered and redirected by the free electrons, unable to travel far. The cosmos, though radiant, was shrouded in fog. Our helium nucleus floated in this brilliant storm, unaware of what lay ahead. There was no up or down, no direction, only motion. A dance of particles in a glowing soup that stretched as far as existence itself. But time brings change, even to the most extreme environments. As the universe expanded, its heat dispersed. And when the temperature fell to just a few thousand degrees, Kelvin, roughly 380,000 years after the beginning, something extraordinary happened. The energy of the universe became too weak to rip electrons from nuclei. And so, at last, atoms formed. The universe became neutral. This event is known as recombination, but it was more than a simple chemical milestone. It was the first great transformation of the cosmos. With electrons locked into atoms, light was finally free. Photons, once imprisoned in the plasma fog, now streamed freely through space, creating the first clear view of the universe. We can still detect that ancient light today. It is the cosmic microwave background, the afterglow of creation. Yet, paradoxically, with light finally liberated, the universe itself grew dark. The shining plasma faded, and no stars had yet formed to take its place. This was the birth of the first true darkness. In this new epoch, known as the Cosmic Dark Age, gravity began its quiet work. Invisible structures, made of dark matter untouched by light, started to clump together under their own pull. These dark halos became seeds for galaxies, stars, and everything that would follow. Ordinary matter, including our helium atom, fell into these invisible wells, following the gravitational script written by the unseen. Yet, unlike dark matter, gas could cool and radiate energy. It could collide, compress, and collapse. And somewhere, hidden deep within a dark matter halo, our future proton was now nestled in the cold beginnings of a cloud that would one day shine. For millions of years, the universe lay in wait, silent, empty of stars, yet rich with potential. The darkness was not the end, but an interlude, a breath before the first light. Our proton, still locked within its helium home, drifted through this cosmic night. It had survived the chaos of the early universe, the fire and fury of the first seconds, and now floated quietly through the silence. But this stillness would not last. Soon, gravity would collapse gas into blazing new furnaces. The long night would end, and with it, the universe would awaken once more. The story of light was about to begin. After the long silence of the cosmic dark age, the universe was ready to shine again. Slowly, gravity pulled cold clouds of hydrogen and helium into dense knots within the invisible scaffolding of dark matter. These knots collapsed under their own weight, heating as they shrank, until their cores reached temperatures of millions of degrees. And deep inside one of these collapsing clouds, our helium atom, home to our ancient proton, was caught in the swirl. For the first time since its birth, the proton found itself on a new journey, falling inward toward the blazing heart of something never seen before, a star in the making. This was no ordinary star. It was among the first. Born when the universe was just a few 100 million years old, it was massive, unstable, and short-lived. Unlike the stars that would follow, these primordial giants were pure, made almost entirely of hydrogen and helium, untouched by heavier elements. Inside their cores, nuclear fusion roared to life, transforming hydrogen into helium and unleashing a radiant energy that pushed outward against gravity's crushing pull. Light burst forth for the first time in cosmic history. The darkness ended, and the stars were born. In one of these stellar furnaces, our proton was carried upward by immense convection currents, bathed in energy, but far from the fusion deep inside. But stars, like all things, have limits. The immense mass that gave the first stars their power also sealed their fate. After only a few million years, their hydrogen fuel began to run low. Gravity, ever patient, pressed inward again. In response, the star ignited new fires. Helium became the next fuel, and deeper within, the stellar core transformed it into carbon, then oxygen, then heavier and heavier elements. With each burning layer, the star aged rapidly. And finally, when the core became iron, a nucleus that yields no more energy through fusion, the star met its end. Its collapse was sudden. Its death was violent. In a flash brighter than an entire galaxy, the star exploded. A supernova. Shockwaves raced outward, temperatures soared. The very fabric of atoms was torn and rearranged. In those brief, final moments, new elements were born. Gold, silver, uranium, scattered like stardust across the cosmos. But our proton, still nestled within its helium nucleus, survived the inferno. It was flung into interstellar space, riding the wave of cosmic debris. For the first time, it was free again. The star that once held it together had vanished, leaving only glowing gas and scattered ash behind. Yet the proton's journey was far from over. Ejected into the cold between the stars, the proton drifted through clouds, enriched with the ashes of the dead. But the universe was not done building. Over time, gravity worked once more, gathering matter into new clouds, forming new stars. Again and again, our proton was drawn into these celestial rebirths. Sometimes it found itself deep in the core, helping fuel the fire. Other times, it remained in the outer layers or in newborn planets orbiting far from the heat. Through each cycle, it watched the universe evolve, stars forming, burning, dying, each one leaving its mark on the cosmos. And in every turn of this stellar wheel, our proton played its quiet part. The death of a star is never the end. In its destruction, a new beginning is born. The universe is not wasteful, it recycles. The gas and dust hurled into space by dying stars do not drift aimlessly forever. They gather once more into clouds, they cool, they collapse, and from their collapse, new stars ignite. In this endless rhythm, the universe slowly transforms. The early stars forged only helium and trace elements, but their deaths seeded the cosmos with heavier ingredients. Each generation of stars inherited this legacy, adding to it with every nuclear breath. And through this slow alchemy, the universe became chemically richer. Our proton, once part of a helium atom, was drawn into one of these new stellar nurseries. But this time, the cloud was different. It carried dust laced with carbon, oxygen, silicon, and iron, elements born from stars long gone. As the new star began to form, our proton was no longer destined to remain in helium. It was captured in a nucleus of carbon, forged in the heat of a newly burning star. This carbon would go on to travel far from the core, carried by stellar winds, embedded in the outer layers, drifting with the rising pulses of energy. In time, these pulses became so violent that they expelled much of the star's atmosphere into space. Now, the proton, part of a carbon atom, was set adrift once more. The star that birthed it had become a white dwarf, its core a smoldering ember of dead matter. Meanwhile, the expelled gas cooled and mingled with the interstellar medium. Again and again, the cycle repeated. Clouds formed. Stars were born. Some were massive and brief. Others, like our Sun, lived longer, more stable lives. In one such star, the carbon atom joined again in the dance of fusion. But this time, its journey would take a different path. Rather than burning in the core, the carbon drifted outward into a swirling disk of dust and gas, the birthplace of planets. Within that disk, pieces of rock and ice collided, merged, and grew. The carbon atom became part of a rocky world, a newly formed planet circling a yellow star. The world cooled, water flowed, and chemistry began its silent work. Life emerged, simple at first, then complex. And somewhere within a leaf, or a strand of protein, or a breath of air, our proton found itself participating in something new, something fragile and extraordinary. No longer just matter, it was now part of a living system. And while it could not know this, the universe had changed. Through the evolution of stars and the deepening chemistry of matter, life had become possible. But even life is not an escape from the cycle. Organisms die, mountains rise and fall, oceans dry and return, and the elements that form them are returned to the earth, to the stars, to the sky. The carbon atom was buried, pressed into stone, transformed into diamond, then lifted again, shining briefly before being lost once more. The proton within it remained unchanged, eternal amid the transformations. And always, it waited. Waited for the next call of gravity, the next wave of energy, the next star to ignite. It had become a traveler in a cosmos of fire and silence, light and shadow, a witness to the alchemy of time. Around 5 billion years ago, a swirling cloud of gas and dust collapsed under its own gravity. This was not the first time such a collapse had occurred in the universe, but this one was different. At its center, a new star was born, yellow, warm, and stable. We would come to call it the Sun. Surrounding it, in a flattened disk of material, fragments collided and merged, slowly forming the planets, moons, and smaller bodies that would become our solar system. In this disk, among rocks and ice, was a carbon atom, our proton, drifting once more, waiting to find its place in something new. As the young planets grew, one world in particular took shape in the right place, neither too hot nor too cold. It was the third planet from the Sun, and its destiny would be unlike any other. The Earth. Still molten at first, bombarded by leftover debris from planetary formation, the surface eventually cooled. Water arrived, likely delivered by icy comets, and began to pool in great oceans. The carbon atom, embedded in the crust, was eventually released and joined with other atoms to form complex molecules. These molecules, guided by chemistry and time, became the seeds of life. Life on Earth began humbly. Simple, single-celled organisms dominated for billions of years. They fed, divided, and adapted, their molecular engines driven by elements like hydrogen, oxygen, nitrogen, and carbon. Our proton became part of one of these cells, woven into the machinery of life. It helped build sugars, proteins, and the backbone of genetic code. Over time, life diversified. Some cells learned to harness sunlight, producing oxygen and transforming the planet's atmosphere. Others began to organize into colonies, laying the groundwork for the rise of multicellular beings. The carbon atom, still carrying our proton, moved through the oceans, through the food chains, through the bodies of countless microscopic creatures. And then, as life ventured onto land, it joined a new form, a plant. Perhaps a fern waving in the breeze, or a primitive flowering species on the shores of an ancient sea. The plant, in turn, was consumed by something else, a small creature perhaps, or a large one. And so the proton continued its passage through life. It moved from one organism to another, passed through breath and blood, flesh and soil, a silent participant in evolution. Time moved forward, as it always does. Life changed, rose and fell. Dinosaurs ruled and vanished. Mammals rose in their place. Ice ages came and went. And then, in a brief moment, a flicker in cosmic time, humans appeared. Our ancestors walked upright, formed tools, lit fires, and looked up at the stars with wonder. The carbon atom, still holding the same proton born in the fires of the early universe, now became part of a living human. Perhaps it rested in a muscle, or traveled in a breath, or dwelled within a brain that pondered its own existence. From stardust to thought, that was its journey. But life is fragile, and it is fleeting. The carbon atom did not remain in the same form for long. The body it once inhabited died, decayed, and returned to the earth. Buried beneath layers of soil and rock, it was compressed over time into minerals, or perhaps once again became a diamond, a crystal lattice of carbon forged in pressure and darkness. And like before, it would remain hidden, until one day, perhaps, it was found, cut, polished, and set into a ring, admired, lost again. The proton traveled on, unknowing and unchanged, while the story of life continued to unfold around it. And all the while, the sun shone on. For billions of years, it burned steadily, fusing hydrogen into helium at its core, giving light and warmth to the planets that circled it. Earth, unique among them, blossomed with forests, oceans, and life. The solar system itself was just one among hundreds of billions in the Milky Way, and yet it was here, on this pale blue dot, that the universe found a way to look back at itself. Through eyes, through thought, through stories like this. And somewhere, deep within those stories, traveled one quiet proton, unchanged, eternal, and still moving forward. Nothing in the universe lasts forever, not even the sun. Though it has burned steadily for billions of years, quietly powering the miracle of life on Earth, its fuel is finite. Deep within its core, hydrogen is slowly running out. One day, that quiet engine will begin to falter. As the core contracts under gravity, the outer layers will respond with fury, swelling outward. The sun will grow enormous, transforming into a red giant. Its radius will extend far beyond its current boundaries, and the inner planets, Mercury and Venus, will vanish into its searing depths. Earth will not be spared. Long before our planet is consumed, the increasing luminosity of the sun will scorch the atmosphere. Oceans will boil, magnetic shields will fail, and the surface will burn beneath relentless solar winds. Mountains will melt. Cities, if any remain, will be swept away. The carbon atom that once held our proton, perhaps now part of a diamond buried in Earth's crust, will be dislodged. In the chaos, it will be flung into the expanding solar atmosphere. It will not burn, for the temperatures are not yet high enough to destroy atomic bonds, but it will be swept into the inferno that was once the sky. As the red giant stage reaches its climax, the sun will become unstable. It will pulse with enormous energy, expelling its outer layers into space in great waves of glowing gas. What remains at its center is a white-hot core, a white dwarf. This is the final form of our sun, a star without fire, supported not by fusion, but by quantum pressure. It will shine not with power, but with the residual heat of its former glory. The material it cast off, carbon, oxygen, remnants of Earth, will drift outward, joining the interstellar medium once more. Among them, our proton, forever unchanged, adrift again in the cold. The solar system as we knew it will no longer exist. Planets will be either destroyed or abandoned in silent orbits around a dying star. The brightness of the sun will have faded into a ghostly glow. For a time, the white dwarf will remain warm, a beacon in the dark. But as the eons pass, it too will cool, slowly fading toward blackness. It will never collapse further, never explode, never burn again. It will simply wait, a relic of a star that once nurtured life. Around it, the remnants of its planets will scatter, and the sky that once teemed with possibility will be silent. And yet, even in this end, the proton endures. It has survived creation, fire, life, and the death of a planet. Now it floats through a quieting galaxy, untouched by the fate of worlds. It is no longer part of Earth, no longer warmed by sunlight. It is a wanderer in the void. And though the Earth is gone, and the sun is only memory, the story of the proton continues, carried on starlight, held in silence, moving ever forward through the darkening cosmos. The golden age of stars, when galaxies blazed with light and the heavens sparkled with creation, will not last forever. With every passing epoch, the universe grows older and dimmer. The brilliant stars that once lit up the cosmic tapestry are slowly extinguished. Massive stars burn fast and die young, leaving behind neutron stars and black holes. Sun-like stars, too, eventually become white dwarfs. While new stars continue to form, the fuel they require, cold hydrogen gas, is slowly being consumed or locked away in the corpses of dead stars. The universe, like a fire burning through its last embers, begins to fade. Over trillions of years, the rate of star formation drops to near nothing. No more great clouds collapse, no more brilliant stars are born. What remains are the dimmest of all stars, red dwarfs. These small, cool stars burn their hydrogen slowly, stretching their lifespans across hundreds of billions or even trillions of years. They are quiet, enduring beacons in a sky that grows increasingly dark. Our Proton, having cycled through stars, planets, and even life, finds itself now inside one of these final stars. It is bound within a nucleus of iron, warmed only slightly by the fading nuclear fires of a universe in twilight. These red dwarfs do not die in violent explosions. They do not burst into supernovae or collapse into black holes. Instead, they simply fade. As their fuel runs out, they cool and dim, turning into black dwarfs, stellar remnants so cold they barely emit any heat or light. When the last red dwarf exhausts its final reserves, the universe will fall into darkness. There will be no new stars, no new light. The Milky Way will become a cemetery of stellar remnants, white dwarfs, neutron stars, black holes, and black dwarfs, drifting silently through the void. Our Proton remains inside one of these dead stars, now a black dwarf, colder than the deepest night. No light escapes it, no radiation glows from its surface. Yet even here, matter is not entirely still. Quantum mechanics tells us that particles are never truly at rest. Inside this dark stellar husk, atoms jitter with the faintest flickers of motion. Over immense spans of time, these motions may lead to strange and subtle transformations. But for now, the Proton waits. The universe around it is quiet, colder than ever, and stretched thin by the continued expansion of space. The galactic dance slows. Fewer stars remain bound to one another. Some remnants are flung into deep space by gravitational encounters. Others spiral inward toward the center of their galaxy, where supermassive black holes still lurk. The Milky Way, once alive with billions of shining stars, contracts slowly as energy dissipates. The Proton star may be one of those ejected, set adrift in the void, alone among nothingness. Or it may fall inward, drawn toward the galactic core, inching ever closer to its final fate. But even in this stillness, the story is not yet done. The age of stars has ended, but the universe continues. Now the cosmos belongs not to light, but to shadows, to black holes and fading embers, to particles like our Proton, forgotten, enduring, ancient. It has witnessed the birth of galaxies, the rise of stars, the emergence of life, and now the dimming of all. It has traveled far, yet finds itself alone in a universe nearing its final chapters. This is the end of the age of stars, and in the silence that follows, a deeper transformation begins, one that will reach to the very foundations of matter, and even time itself. The stars are gone, the galaxies are quiet, the great luminous age of the universe has ended, leaving behind only shadows. Black holes, white dwarfs, neutron stars, and cold black dwarfs drift silently in the growing dark. Our Proton, locked within the core of one of these dead stars, is now a part of a black dwarf, a stellar corpse as cold as the cosmic background, radiating almost nothing, seen by no eye, felt by no light. But even in this silence, nothing is truly still. The laws of physics, ever patient, continue to work beneath the surface in ways too subtle for early minds to imagine. Quantum mechanics tells us that particles are never completely at rest. Even in the coldest, most lifeless corners of the universe, there remains a whisper of movement. Inside black dwarfs, atoms still vibrate slightly, and occasionally, electrons are jostled loose. These escaping electrons, once gone, are not replaced. Slowly, over unimaginable timescales, this process chips away at the structure of matter. A proton here, an atom there, evaporating into the void. The black dwarf loses mass, becomes even colder, even darker, until it is only a ghost of its former self. The space surrounding these ancient remnants continues to stretch. Dark energy, the silent and mysterious force accelerating the universe's expansion, grows in dominance. As galaxies drift apart beyond each other's reach, matter becomes increasingly isolated. Our proton, long since ejected from its stellar tomb, now floats alone in the vast blackness. It no longer belongs to any structure, any system. The Milky Way has evaporated, its stars consumed or scattered. The universe, now hundreds of trillions of years old, is a desert of cold particles and endless space. Time flows on. A trillion years pass. And through all this, the proton endures. The fundamental unit of matter, thought to be unbreakable by ancient physicists, still exists. But even the proton may not last forever. Deep in the equations of grand unified theories lies a haunting possibility: proton decay. According to some predictions, protons may not be truly eternal. After an incomprehensible span of time, they may suddenly disintegrate, releasing lighter particles like positrons and photons and vanishing into radiation. No one knows if proton decay truly occurs. To the early minds of the 21st century, it was still theoretical, something not yet confirmed in laboratories or deep beneath the earth. But if it does happen, it will become the final chapter in the history of matter. One by one, across the vast black sea of space, protons will wink out of existence. Not in a flash or a roar, but in a quiet, individual disappearance. The building blocks of atoms will dissolve, and with them, the last remaining structure in the universe will unravel. Imagine this moment, not a singular event, but a slow, eternal process. A universe that once burst forth with stars and galaxies, now watching as its very atoms vanish into the void. No planets, no molecules, no stars, no light, only rare photons and lone electrons racing through space that expands faster than their ability to catch up. Our proton, so ancient, so constant, finally reaches its own end. After a journey through stars, through life, through planets and death, it quietly decays. In a single instant, it is no more. With the decay of the last protons, the universe enters a new phase, a sea of subatomic particles and radiation drifting endlessly. This is not destruction as we once understood it. It is a dissolution, matter melting into a formless nothing, structure fading into the background noise of existence. There is no more chemistry, no more physics as it once operated, no more bonds or reactions or form. The universe has become a nearly featureless void, where the very concept of thing no longer applies. And yet, even here, there are echoes. The fading glow of particles, the distant hum of entropy growing ever higher. Time has not stopped, but it has little left to measure. With no change, no structure, time becomes almost meaningless. The universe is not dead in the conventional sense. It has not collapsed, nor burned, nor shattered. Instead, it has emptied itself, released its potential, and reached a state of maximum disorder. This is the heat death, not of fire, but of silence. But let us not mourn, let us remember. That proton was part of stars that once lit the heavens. It danced in the birth of galaxies, swam through oceans on a living world, and was woven into the breath of a creature who once looked up at the night sky and asked why. It survived explosions, collisions, and the final quiet of the cosmos. Its death was not a failure, but a fulfillment. It completed its arc through time, and as the last particles fade into stillness, the universe waits, not for resurrection, but perhaps for reinvention. In the vast, cold stillness of a future where even stars have become memories, where time stretches without purpose and light has long vanished, only a few building blocks remain. They are scattered remnants of everything the universe once was: electrons, neutrinos, and above all, protons. These silent particles, forged in the first millionth of a second after the birth of the cosmos, have endured longer than galaxies, planets, and life itself. Our proton, which once drifted through the core of stars, through living cells and dying worlds, now floats alone in a void that has forgotten light. It is easy to believe that protons, so enduring, are truly eternal. For ages beyond imagination, they have resisted change. But deep within the mathematics of the universe lies a different possibility, an unsettling truth whispered by grand unified theories. According to these models, protons are not immortal. They live unimaginably long lives, yet even they may decay. A process so rare that not even the oldest black holes live long enough to witness it often. And yet, with time stretched into trillions upon trillions of years, even rare events become inevitable. Proton decay is not an explosion. It is not violent or dramatic. There is no warning. It happens silently, invisibly, and within a single instant. A proton that has existed since the beginning of time simply ceases to be. It transforms, its energy dispersing into lighter particles such as positrons and photons. It leaves behind no trace of its once intricate structure. The most stable form of baryonic matter disappears into radiation, and with it, a final link to the tangible universe is severed. It is the quietest death in all of time. When the last proton decays, the universe will cross a threshold unlike any before. For the first time since its birth, there will be no more matter, no atoms, no chemistry, no possibility of forming structure. The very foundation of physical reality will have been dissolved. The universe, once a place of stars and fire, of life and wonder, now consists only of ghostly particles, massless, featureless, and adrift. The decay of the final proton marks not just the end of a particle, but the conclusion of the material universe. Our proton, whose journey we have followed from the beginning, has seen it all. It was born in the primordial light, helped build stars and planets, coursed through living beings, and survived the collapse of its host star. It drifted through deep time, through the dark age of entropy, witnessing the silent fall of the universe into nothingness. And now, at the edge of eternity, it too must vanish. In the blink of a cosmic eye, the final proton decays, and the last trace of matter is gone. Its story ends, not with a sound, but with a breathless silence. There is something beautiful, even poetic, in the quiet passing of the final proton. It reminds us that nothing, not even the building blocks of matter, escapes the flow of time. Yet it also reminds us of the grandeur of existence, that a single proton could travel across the history of the universe, witnessing its creation, its blossoming, and its decay, is nothing short of miraculous. And though it is now gone, the memory of its journey remains, etched in the story of the cosmos itself. The universe is dark, empty, and silent, but its story, somehow, is not yet over. Long after the stars have faded, after matter has unraveled, and the last protons have silently decayed, the universe remains populated by its final titans, black holes. These are the remnants of a more luminous time, formed from the collapse of massive stars or the merger of cosmic giants. For trillions upon trillions of years, black holes have remained unchanged. Dark, dense, and silent, they are the most extreme objects in the cosmos, regions where gravity becomes so overwhelming that not even light can escape. And yet, they too are not forever. From the outside, a black hole appears eternal, an invisible wound in the fabric of space-time. But deep within the mathematics of quantum physics lies a quiet rebellion. In 1974, physicist Stephen Hawking made a discovery that shook the foundations of our understanding. He proposed that black holes are not completely black. Due to quantum effects near the event horizon, they emit a faint glow of radiation. This phenomenon, now known as Hawking radiation, implies that black holes are not immune to time. They too slowly evaporate. The source of this radiation is not from within the black hole, but from the quantum vacuum just outside its boundary. Space is never truly empty. Even in perfect darkness, Virtual particles continuously flicker into and out of existence. Near the event horizon, one member of a particle pair may fall in, while the other escapes, stealing away a tiny bit of the black hole's mass. Over eons, this slow siphoning of energy results in mass loss. The black hole shrinks, imperceptibly at first, but steadily. It begins to fade. This process is slow, almost unimaginably so. A black hole with the mass of a star may take more than 10 to the power of 67 years to evaporate. The larger the black hole, the slower the loss. Supermassive black holes, found at the hearts of galaxies, can take a googol of years, a number so vast it defies human intuition. For much of the universe's future, these giants will be the last anchors of structure, the last prisons of matter, the last sources of gravity. But even they cannot resist forever. Hawking radiation will claim them all. As a black hole loses mass, the radiation it emits grows stronger. The smaller it becomes, the faster it evaporates. Eventually, its temperature skyrockets, and its death accelerates. In the final moments, what was once a silent well in space becomes a brief, brilliant flare, a burst of energy unlike anything else in the dark cosmos. This is not an explosion in the traditional sense, but a final whisper of existence as the black hole vanishes completely. The event horizon dissolves. The singularity is no more, and another piece of the universe becomes memory. With each dying black hole, the universe grows dimmer still. When the last of them evaporates, space will hold no mass, no gravity wells, no heat or light. It will be a sea of low-energy photons, neutrinos, and fading ripples of entropy. The grand architecture of galaxies, stars, and planets will be gone. All that remains is expansion, driven endlessly by dark energy. And yet, in the evaporation of black holes, the universe experiences its final flickers of transformation. These are the last thermodynamic transactions, the final releases of energy into a cosmos otherwise motionless. And so, the giants fall. Not with thunder, but with a slow and graceful bow to the laws of quantum mechanics. The same universe that once gave rise to fire and stars, to life and awareness, now watches its most enduring structures dissolve into light. The death of a black hole is the death of gravity's last stronghold. And when the last one fades, the story enters its quietest chapter. A universe once filled with brilliance and structure has become smooth, silent, and near featureless. But perhaps, in the quantum fog of emptiness, something new waits to emerge. The universe now lies in a state of deep and final silence. The stars have faded, the matter has unraveled, the black holes have evaporated. What remains is a cold, dark sea of low-energy radiation, drifting particles, and the ever-stretching fabric of space. No more light shines, no more gravity binds. There are no atoms, no galaxies, no structures of any kind. Time itself has lost its rhythm, for nothing changes, and there are no clocks left to count its passage. The cosmos has become a near-perfect void, quiet, simple, and seemingly complete. And yet, there is something still lurking within this emptiness, a mystery that has shaped the fate of the universe since its earliest days. It is the strange and invisible force we call dark energy. For billions of years, dark energy has driven the acceleration of the universe's expansion. It is not matter. It is not light. It does not dilute as space grows. It is a field of energy that remains constant, indifferent to the thinning of all else. And though we do not fully understand it, some believe this quiet field may not be as stable as it seems. In quantum physics, stability is never guaranteed. Even a system that seems constant can, through a process called quantum tunneling, suddenly shift into a lower state of energy. Some cosmologists wonder if dark energy itself may one day decay in this way, not in a slow fade, but in a sudden transformation. If this occurs, the universe as we know it would be wiped away in an instant. The vacuum of space would reconfigure, its properties rewritten, and the laws of physics themselves may change. It would be the end of this universe, but perhaps the beginning of something else. This kind of event has a name: vacuum decay. It is a theoretical possibility buried deep within the structure of quantum fields. If it were to happen, a bubble of lower energy vacuum would appear somewhere in space and begin to expand at the speed of light. Everything it touched would be transformed. Particles would dissolve, forces would shift, and nothing that existed before could survive. To an outside observer, it would be as if reality had been erased and rewritten before the eye could even register the change. But from this destruction could arise a new creation. In the searing energy of a newly reformed vacuum, space could boil with new particles, new fields, new possibilities. A fresh Big Bang, not in time, but in potential. A universe that begins again, not as a continuation, but as a rebirth. New stars might form, new matter might coalesce, new laws might govern how energy and particles behave. It may resemble our universe, or it may be something entirely different, something stranger, wilder, perhaps even richer in possibilities than before. And so, as the universe lies in what appears to be its final sleep, we must ask, is this truly the end? Or is it simply a breath between eternities? The decay of dark energy, though distant and uncertain, offers a vision not just of death, but of transformation. Perhaps this is how the cosmos renews itself, not through preservation, but through reinvention. A cycle not of life and death, but of forgetting and becoming. And if that is true, then from the quiet stillness of now, the fire may rise once again. Imagine a circle so vast, it spans not just space, but time itself. A loop with no clear beginning and no definitive end. The universe, as we have seen, began in light and will end in silence. It rose from a singular moment of creation, evolved through complexity, and dissolved back into simplicity. But perhaps this is not a final curtain. Perhaps this long arc of time, this story from nothing to everything and back again, is just one breath in a larger pattern. A rhythm that beats beyond human lifetimes, beyond even stars, echoing across aeons. In the beginning, there was darkness. Then came light, then matter, then life, then thought, then silence once more. This progression mirrors something ancient, something almost mythological, a cosmic wheel turning through cycles of birth, growth, decay, and renewal. It is a pattern we see in all things, in the lives of stars, in the rise and fall of civilizations, in the seasons of our own planet. Even within ourselves, we sense the truth of impermanence. Everything changes, everything returns, and maybe everything comes back again. If dark energy decays, if space itself resets, then the universe may be reborn. And in that rebirth, perhaps protons will once again emerge. Perhaps stars will form. Perhaps life will rise anew. Not a continuation of what was, but a new version. A different arrangement of the same fundamental ingredients. In this way, the cosmos is not just a one-way journey from order to entropy. It may be a self-renewing system, a grand experiment running again and again, trying every possibility, every variation, until something truly eternal is found. And what of us, beings made from stardust, from ancient protons, from time itself? We are witnesses to one brief turn of this cosmic wheel. Our thoughts, our dreams, our stories, they are flickers in the darkness, and yet they are part of the pattern. Perhaps it is through consciousness that the universe becomes aware of its own cycles. Perhaps the longing we feel to understand the beginning and the end is not accidental. Perhaps it is a memory, deep, buried, and cosmic, of the countless loops that came before. In the end, the story of the universe is not just about energy and matter, or stars and galaxies. It is about change, about return, about the silent promise that even when all seems lost, something new may rise from the ashes. If the universe is a loop, then this is not a story of death, but of becoming. A reminder that in the grand architecture of time, endings are only beginnings wearing a different face. The proton returns to the void returns to light, and the wheel turns again. If you enjoyed this video, please give it a like and subscribe to our channel. Let us know your thoughts in the comments. We'd love to hear from you. Thanks for watching, and we'll see you in the next one.